In this module, we will talk about forces and analysis of structures and machines. A structure consists of a series of connected structural members or rigid bodies designed to support loads or forces. Loads may be either stationary or moving, but the structure is usually at rest. If the structure is moved, the motion is executed slowly. Machines are made up of several connected elements designed to transmit and transform loads or forces rather than support them. The machine generally has moving parts. With structures and machines, we must determine external forces acting on them and the forces that hold the parts together. We will first talk about simple plane trusses. A truss is a structure usually consisting of straight uniform bars or members arranged in a series of adjoining triangles. They are fastened together at their ends to form joints. Joints may be pinned, welded, riveted, bolted, or nailed depending on the type of truss. Trusses may be used for such things as bridges, towers, and buildings. In most cases, a truss has two general purposes: to distribute any applied loads among the many members of the truss, or to span greater distances than allowed by the longest single member in the truss. To simplify calculations, we make three assumptions about the simple plane truss. The first assumption is that the bars are connected at their ends to form joints that behave like frictionless pins. This first assumption represents a substantial departure from the real truss. The ends of the members are attached to each other so that bending of the member must occur. The forces in the members calculated based on pin construction do not differ substantially from their true value. The second assumption is that all forces acting on the truss are applied at the joints. This is justified in most practical cases. Except for the weight of a member that acts at its center of gravity, loads are usually transmitted by other structures or members to the joints of the truss. The weight of a member is small in comparison with other loads on the truss and can be either neglected or divided equally between the joints at its ends. The first and second assumptions ensure that all bars are two-force bodies or members. The third assumption is that the members' joints and loads all lie in a plane. Each member must be either in tension or in compression. The third assumption ensures that we have a problem in plane statics. To construct a simple truss, start with the simplest rigid structure consisting of 3 bars and 3 joints, triangle ABC. By adding pairs of bars, AD and CD, the structure remains rigid. To rigid structure ABCD, add the pair of bars BE and DE, and the structure remains rigid. The process is continued until the truss is complete. The term rigid means the truss functions as a whole, like a rigid body. The trusses shown here were all constructed in this manner. Shaded triangle ABC has been taken as the starting point for each truss. Adding pairs of members CD and BD establishes joint D. The addition of each new pair of members establishes the remaining joints. The trusses shown are all simple trusses. Whatever the complexity, the structure's ability to distribute loads amongst its members depends on the shape of the truss and the points at which loads are applied. The size of the truss, link material, and cross-sectional geometry of the links do not affect the load carried by any individual link. Consider the Warren truss shown here. The pin joints are labeled A, B, C, D, and E. The member joining pins A and B is referred to as AB. The force in the member is FAB. Using these symbols, the free body diagram for each truss is shown. All members of the truss are shown in tension. If the member is in tension, equilibrium equations give a positive value for the force in the member. If in compression, the equations give a negative value. Between each joint and member, the forces are in opposite directions. The force of member AB on joint A is equal in magnitude and opposite in direction to the force of joint A on member AB.